And so chapter 3 deals with thermodynamic properties. And it's mainly thermodynamic properties of pure substances. Now, the textbook does of pure substances, but when you're an engineer, you're not going to just be looking at pure substances. You're going to have complex materials. But we'll just deal with mainly pure substances. So let's introduce what a pure substance is. I didn't want to write all this out, but I guess I'll do it. A material that retains its chemical, molecular structure, composition, when going from one equilibrium state to another equilibrium state, say state 2. So, material that retains its chemical, molecular, composition structure. So nitrogen gas, and let's just consider one state is one temperature and the other state is another temperature. So if I consider nitrogen gas at room temperature versus nitrogen gas at 50 degrees C, does the chemical or molecular structure of N2 change? No. So it can be considered, yes, it's a pure substance, air. So it is a pure substance. Now let's look at air, and let's look at it in the classroom versus the top of Mount Everest. Now, those are two different equilibrium states, right? So we would have to say that air was not a pure substance when we brought it from here to here, because we'd have to change the chemical composition, and we know that the chemical composition of air is much different at the top of Mount Everest. But still, in general, we want to just say that air, it doesn't change. We're going to say that the percentage of hydrogen, oxygen, nitrogen, all these other things doesn't really change. And we're not getting molecular hydrogen into atomic hydrogen, and we're not doing, these chemical reactions. So N2 stays N2. It doesn't become N and N. Now let's look at this one. So now let's say I have water in the vapor form and water in the liquid form. And now I have a container that contains both water vapor and water liquid. Can I consider this a pure substance? Yes? Any no's? No no's? Okay, so it is. So on that case, I have air and liquid, so I can say that this is again water, and then I have air up here. So can I consider this a pure substance? Yeah, no. Because it's not all one thing, right? Here I kept it with H2O everywhere within. Here I kept it all air. Here I kept it all N2. Okay, so coupled with that, I can have phase changes of pure substances. So this would be my gaseous state. This would represent a solid state. This right here would represent a liquid state. Okay, and let's just say that each one of these atoms is copper. We're all familiar with solid copper. We're not so much familiar with liquid copper, and we're even less familiar with vapor copper. But given that copper is a pure substance, it can be in any one of these phases. It just turns out we have to be above 600, well actually more than that, 800, I think 800 Kelvin or 800 C to bring it to liquid state. And then it's really high temperature to bring copper to a vapor state. but I can have phase changes of a pure substance. We're more familiar if I say that if I were to put like a little, make all these water molecules. So instead I make them all water molecules, then this would be ice, this would be liquid water, and this would be water vapor. And we're familiar with the phase change of that. But right now we're going to just say that, you know, it's copper and go through these phase changes. So according with each one of these, there's thermodynamic properties of each state. So what is one of the key thermodynamic properties? Let's think first law. Let's think built-in to temperature in the first law. Internal energy, so a thermodynamic property, internal energy. And in that case, I can have big U or small u, where small u is equal to big U divided by m. Let's think second law. What's another thermodynamic property? Entropy. I can have big S or small s, and coupled with that, small s is equal to big S over m. Now, so there's an internal energy and there's an enthalpy associated with this solid copper. There's internal energy and there's an entropy associated with this liquid copper. There's internal energy and there's an entropy associated with this gaseous copper. And both internal energy and entropy are equations of state. So if I just know the temperature and pressure and the phase of my copper, I can find, someone has documented, or I know that I can define that based off the state postulate, two independent intensive properties, I can find the state of the system. So if I know its temperature and pressure, and I say it's solid at that temperature pressure, I know its entropy and internal energy. Likewise, temperature and pressure, know its internal energy and entropy, internal energy and entropy. Now the third one which gets introduced, the third thermodynamic property, is called the enthalpy. And the enthalpy uses H, or small h, where small h is equal to big H over m. So small h, enthalpy per unit mass. And so this is a new property. Now when it comes to phase change, which I've illustrated here, the enthalpy ends up being quite useful. So we introduced this idea of enthalpy and changes in entropy, because if I go from solid to liquid, this is also a state function, enthalpy. So given I know its temperature and pressure, I know its enthalpy, I know its internal energy, I know its entropy. If I go from here to here, I can get the change in enthalpy. And it turns out when I have a pure substance and I go from solid to liquid, the change in enthalpy is going to be related to its mass times the latent heat of fusion. If I go from liquid to vapor, the change in enthalpy from going from liquid state to gaseous state of copper is going to be equal to its mass times the latent heat of vaporization. So this change in enthalpy is related to phase change. So how much on this do I want to do? Okay, so more on enthalpy. So I have enthalpy, and I've already said it's a big H, and I already had entropy, which is big S. And so in expression form, I have big H is equal to big U plus P V. Likewise, I can write H is equal to small u plus P small v. So entropy, I never really gave you an expression for entropy alone, right? There was only the second law only said a change in entropy. So delta S is equal to integral delta Q reversible over T. And then I had this other one, the tedious question form, TDS is equal to Q. TDS question. And they're related. You can see all I have to do, right, is take this out of integral form and I get it to here. If I divide by T and then integrate it, I end up getting to here. So what is entropy? That's a tedious question.
What was the subscript on
reversible. Here I have a nice expression that relates the enthalpy to the internal energy and the pressure and volume of my system. So if I know it's internal energy, which I need to know temperature and pressure, then I already know it's pressure. Then if I tell you the volume of the system, I immediately know the enthalpy. Well, I don't necessarily need to know that. Really, all I need to know is the temperature and pressure of my system to get the enthalpy. But say I didn't have it tabulated, and I only knew the internal energy. So entropy, internal energy relationships. So I can go Q is equal to delta U minus W. And then I can rewrite that as delta Q is equal to delta U minus dW. And then I have the expression for work. Work is equal to minus the integral of P dV. So I'll put on here for convenience. And so from this, I can go delta work on is equal to minus P dV. So when I have this expression here, I can write it as delta Q is equal to du. And this was a minus sign, and then I have a minus sign over here, so plus P dV. And now I have the second law. So second law, I'm going to use the TDS. T ds is equal to Q. So I can couple this with that. And then I end up getting T ds is equal to du plus P dV. And so here I have some expression coupling entropy and internal energy. And I also can write this as T d small s equals d small u plus P d small v.
For the second equation that you wrote there, the delta Q is equal to delta U, the one to the left of that?
This one here?
No, to the left of it.
Here?
I'll go down. Right there. Is there supposed to be a delta sign?
No, so I made these double deltas into a D. So this is the change, this is the incremental change and change, and so this represents the incremental change and change. But I can rewrite this expression here, to get du is equal to T ds minus P dV, or d small u is equal to T d small s minus P d small v. This ends up being the first, well, this one here, the first TDS relation. So this one here is a coupling between the change in entropy and the change in internal energy in my system. I can do a similar type of thing with the enthalpy. So let's just keep, I'm going to circle this one, this first TDS relationship. So I'm going to keep this in mind. And now let's write out what the enthalpy is. So I already derived this. So H is equal to U plus P V. So I can go to DH is equal to DU plus dPV, which equals du plus P dV plus V dP. And then I can rewrite this to du is equal to dH minus P dV minus V dP. So I have this expression. So all I did is I played around with how I define the enthalpy. Just played around with that. Now I can go back to this expression here, and I can plug this into here. So when I do that, I got T ds is equal to, I'll put a bracket here, dH minus P dV minus V dP. And then I had a plus P dV. And then I can cross these out. And then I get T ds is equal to dH minus V dP. And this here is the second T ds relation. So this one describes how I can get the change in entropy related to a change in enthalpy. So this expression here gives a coupling between the change in enthalpy and the change in entropy. The first TDS was a way to describe the change in entropy to the change in internal energy. So they're just two different expressions. You can see here now I don't have to do this complicated integral with reversible heat. All I really need to know is what the temperature and pressure of my system was at each state, because as soon as I know that, I know what delta U is, or I know what delta H is. Given I know the change in pressure, and I know the volume and temperatures, I can calculate the change in entropy. So let's just rewrite this one. So dH is equal to T ds plus V dP, or ds is equal to dH over T, P equals constant. dH is equal to T ds. So if I have a constant pressure process, then it becomes even simpler. The change in enthalpy is just going to be related to the change in entropy. So if I have a phase change at constant pressure, phase change happens at constant temperature already. So if I have a phase change that happens at constant pressure, constant temperature, if I know what type of phase change, I can look up the latent heat of vaporization, latent heat of fusion, and I can calculate the change in entropy based off that phase change. Was there a question?
Yeah, I was just going to say, please explain a little bit what enthalpy really relates to the nitrogen system and then what exactly.
Yeah, okay, so that's a good question. So I'll go back up to this expression. I'll circle this one here. So the question is okay, so tell me what enthalpy is, right? It was I already told you, you're already thinking enough about what entropy actually is, and now here comes entropy, or enthalpy. So, or actually I want to do the one above, but so when they started doing a lot of work with locomotive engines, that's when the enthalpy really started to become useful, because they were looking at putting in coal, creating steam, letting the steam do work. So sometimes I refer to enthalpy as the thermal work. Sometimes people refer to enthalpy as the work corresponding to phase change. So in that earlier slide, I talked about bringing something from a solid state to a liquid state. And then when I went through this phase change, I said that this change in enthalpy from here to here was related to the latent heat of fusion. So if this was ice and this is water, all I need to know is the mass of the ice cube and look up the latent heat of fusion, the energy for that phase change per unit mass, and I can get the enthalpy. So in order to go from a solid state to a liquid state, for a phase change, you could have either endothermic or exothermic reactions. So for an endothermic reaction, heat is required for the reaction to take place. For an exothermic reaction, an explosion, heat is given off. Heat is a product. So enthalpy is coupled with phase change and the directionality of heat. So you can think of it as thermal work, the amount of heat, the work you require to add heat to a system to make it go through a phase change. So there's a few different ways you can look at it. One, thermal work. Another one, phase change work. And then there's another one is flow work. So if I have fluid flowing in a pipe, there's this delta P. So if I go back up to here, say if I have a fluid and I'm making it flow through a pipe, and let's say that the temperature doesn't change as it's going through the pipe, but I have to apply a pressure to get it flowing through the pipe. So there's this pressure that I have to apply to get it to flow. So you can see there's a lot of different ways you can describe what enthalpy is. So flow energy for fluids flowing. Take a pipe, or I want to pump water from a lake to the top of a water tower. There's going to be a pressure I need to establish to get it to go up over gravity. And so if I do this at constant temperature and I say that there's very small change in entropy associated with that, the change in enthalpy is going to be associated with that pressure difference to get it up there. Now, I also can look at it in terms of a phase change reaction. So if I go from solid to liquid, the amount of heat I have to add is going to be coupled to the change in enthalpy from going from one phase to the other. So there's a few different ways you can describe it. Yes?
You don't have to have a phase change then to have enthalpy?
No, right here you can just say there's no phase change associated with this. This, all I did is wrote down an expression. Enthalpy is related to the internal energy times its pressure and volume product, or plus its pressure volume product. Yes?
What are the units for enthalpy?
Joules. Right? So this is joules. This is joules. Right? Kilopascals. Right? And so this product ends up being joules. Yeah, it's a form of energy. It's just it's a modified one that has some conveniences in different circumstances. Phase change situations, enthalpy is a convenient term to look at. If you're looking at pumping fluids, sometimes at constant temperature, enthalpy is a convenient parameter to take into consideration. Okay, so this is a key part of Chapter 3, are these bell curves. And so here I have some curve, I'm going to call it a bell curve, and in this case I have pressure versus specific volume. Okay, specific volume. And on this side, or I should say I'll say what's in the center, this is a liquid vapor mixture and then I need to put in parentheses here saturated. Okay?
Professor,
Yes.
is that whole area or just underneath the dashed line?
Everywhere under this curve is a liquid vapor mixture. Everywhere within here is a liquid vapor mixture. This part right here, this side of the line, represents the saturated liquid line. This side of the line over here represents the saturated vapor line. Okay? So here I have a liquid vapor mixture. So if you remember that container where I had water, liquid water and vapor water, so when I had a mixture of liquid water and vapor water, that's what happens in here. So when I'm all the way on this side over here, say I'm at this point right here, in comparison to this point over here, and I can just put a 1 and a 2. So when I'm right here, that means inside my container I have 100% liquid. It's all saturated liquid. When I'm way over here, I have 100% vapor. If I'm in the middle, I'm 50% vapor, 50% liquid. These lines right here, this is pressure, so I could put P1, 2, and I could put some other 3 and 4, right? P3 comma 4. So I have these different pressures, and associated with that, I could put V1, V2, likewise. So these lines here are temperature isotherms.
So as soon as you get to the right of V1, you'll have a little bit of vapor?
As soon as I'm a little bit right here,
You'll start getting vapor?
I have vapor and liquid.
Okay.
So I take a stainless steel container. It's at room temperature. Okay. I can have some water vapor inside. If I get rid of all the other air inside, I just put water inside. No, I have water inside. No other air, nothing else. It's a pure substance inside. I'm going to have some water vapor and some water, liquid water. Now, if I change its temperature, maybe we can do that here in a second. So let's say that this is atmosphere, 1 atmosphere. 3. Okay? This represents 1 atmosphere. First, let me do these temperature isobars, right? Let me. So I have my temperature isotherms, and this is TB, and this is TA, where TB is greater than TA. So higher temperature, lower temperature, and if you look in, it's flat in this region, so I'm at constant pressure, constant temperature. Constant pressure, constant temperature. So now let's take my cylinder and let's fill it with water. And then we're going to say that this is state 3. Okay? And it's all liquid water saturated. So I'm right here. I have my container. I'm not going to consider the walls. I just have a container filled with saturated liquid water. And it's at 1 atmosphere, and it's all liquid, and so I can say that it is, let's just say TB equals 99.5 degrees C. So basically right at the boiling point, but it's all liquid. Atmospheric pressure inside. Or let's just say I decrease the pressure and temperature, and I go to this point right here. I'll do it in red. So I'm going to decrease the pressure and I'm going to decrease the temperature, but I'm going to do this at constant volume. Reduce T and P at constant volume. So when I do that, I'm going to put it as state X. Now I have my system at state X. And now as soon as I did that, and I'll put black as liquid. So in this case, now I have all of this liquid, but now I have some vapor. Liquid, saturated, vapor, saturated. So I have my system, my container, I just filled it with water, and then I decreased the pressure and temperature within at constant volume. I didn't change the volume of my system, and I brought it to here. In that process, what I ended up doing is I converted some of the liquid to vapor. And now within my container, I have like 15% vapor and 85% liquid. No, in general, I did this complicated way. In general, what happens is you have your container at state 3, and you add some heat to it. But when you add the heat, you don't change the temperature of the system or the pressure of the system. All you do is you convert all that liquid to vapor. So if I add heat, then I can go to state 4. So then I'm here. And if I add enough heat, I convert all my liquid water into vapor. And when you go through a phase changes don't happen at constant pressure and temperature. So all I did is go right along this line at my boiling temperature at atmosphere. Okay, so I drew a lot of this stuff here. In this side, saturated liquid, saturated vapor. I'm just a little bit to the right of here. I have some vapor. I'm a little over here. I'm 100% vapor. If I go a little bit this way, I have a little bit of liquid. In this region here, we call this subcooled liquid or compressed liquid. This is not saturated. So if I compress my liquid, I can no longer be in vapor. It's compressed liquid. And then over in this region here is the superheated vapor. So anywhere outside of this region, I have a superheated vapor. Anywhere over on this side, I have compressed liquid. This point right here represents the critical point. At this point here, I can't distinguish. So this line represents saturated liquid. This represents saturated vapor. When I'm right at the top, I can't distinguish if I'm liquid or vapor. Yes? What's that?
What line distinguishes between supercooled and superheated?
This is subcooled liquid, everything over here. Or compressed liquid. Everything over here.
So right above the critical point is kind of mixed between both.
Yeah, so compressed liquid, so if I keep a liquid at constant temperature, that's say at TA, and I increase its pressure, I suddenly become compressed. If I pressurize my liquid, I start here at 1, I add pressure, but I keep at constant temperature, I compress my liquid. Or I could look at it as I keep my pressure constant, but if I go over here, that means I have to cool my liquid, because I'd have to have a line over here. And then over on this side, it's similar. So this is superheated vapor, so if I go out here, I go to a vapor, but I increase its temperature at constant pressure. If you notice that this bell curve the width gets smaller and smaller and smaller at the top. So the width of this curve is related to the enthalpy. Remember I said it took a certain amount of heat to go from here to here? So there's more heat that's required to go from here to here. When I get up towards the top, I don't know how much heat to add because I don't know whether I'm liquid or vapor. So there are some new technologies that deal with supercritical fluids, things up here. Yes?
You said that going from 3 to 1.
Well, 3 to X.
3 to X. You decrease also temperature.
Yeah, I decrease the pressure and the temperature.
How, if you're at 3, you have all liquid. I just want to understand how increasing the temperature at that point would get some vapor.
Because I went to X, and so as soon as I'm here, I went to a new temperature. I went from TB to TA, and I went from P3 to P1.
It's because you reduce the pressure also. So you need a lower heat to maintain to have a vapor at a lower pressure.
I tried to give this example, and it wasn't maybe the best one. But I was just trying to illustrate that if I'm here, I decrease the temperature and pressure. So I went down in pressure, and I went to a new temperature isotherm. I'm right here under this bell curve, and given I'm right here under the bell curve, I'm no longer 100% liquid. Now I have some vapor, and that was indicative of these graphs.
And the bell curve is for mostly, this is good for water, but there's not
There's a bell curve for copper. Any pure substance, there's a bell curve.
So there's
Any pure substance, there's a bell curve.
okay, so copper will be,
There's a curve like this for copper. There's a curve like this for silicon. There's a curve like this for platinum. Any pure substance. There's a curve like this for, well, not really for air, but kind of for air. I mean, not really for air, but nitrogen, oxygen, molecular nitrogen, molecular oxygen, molecular helium. Anything we can consider a pure substance typically has a bell curve. So I did this PV1. And I just want to point out this width is related to the change in enthalpy or the amount of heat. So I can do a similar curve. Instead of P, I can do T. So now I have temperature. And I could put different points here, right? And I could have different corresponding. So I'll just put a 1 here and a 2 here. So V1, V2. Here's my specific volume. T1, comma 2. Could put a 3 here again. T3, comma 4. And now these lines in this case represent isobars. So PB, PA, PB is greater than PA. This again is still the saturated vapor line. And again, saturated liquid line. And again, liquid vapor mixture, saturated. And again, critical point. And again, subcooled liquid or compressed liquid. And again, superheated vapor. And so if I'm going to take 100% liquid and convert it at constant pressure and temperature, so you can see here from 1 to 2, the temperature didn't change. Now, when I'm in this region, in order to keep constant pressure, I follow kind of this belt and then I go up. If I go from here to here, I have to add heat to convert my all liquid to all vapor. So the width of this corresponding to the change in enthalpy. As I increase the temperature of my system towards a critical point, the change in enthalpy decreases. And just as a reminder, small v is equal to big V over m. But all liquid, all vapor. So maybe to kind of give some little bit more context on this bell curve. So the curves look a little bit different for different substances, but they exist. So related to that bell curve, here I drew it again, but in terms of PV. And so here's my liquid vapor mixture. And then over here I have my superheated vapor. And over here I have my compressed liquid or subcooled liquid. Up here I have my critical point. If I decrease the pressure, then I can have solid and vapor. If I decrease the temperature, remember the temperature lines did something like this. Okay, so if I come over here, I'm at lower temperature. So if I have a line come across, from way over here, I have to have some line that does something like that, right? So I'm over here, I'm all solid, increase the temperature at constant pressure, I become solid and liquid, compressed liquid, liquid vapor mixture, superheated vapor. So I have this, and you can see this little bar. So now let's take this region here, and okay, so this curve here, I'll put it in orange. Now this is a more above is your more traditional pressure versus temperature phase diagram. And there's two lines here. There's the one where a substance can expand on freezing and a substance can contract on freezing. And so this curve here represents me crossing the line. So if I pick a constant pressure and I draw a line all the way through here, like such. So now I need to draw a line through here. And I need to go through all three of these. So okay. And I'll put an arrow like such. So you can see the width of this curve right here. This whole region, that represents that line, the width of that line. So if I take a magnifying glass and I zoom in to this region right here, what I'm going to see is this bell curve. Because right on this line, oh wait, let me see. I put it in the wrong spot. Sorry. It should be over here. Okay. So if I take a magnifying glass and I zoom in right along that line right there, that's what I see. So when I plot it in this form, it's because when I'm on that line, I can be both liquid and vapor, or all liquid or all vapor. And so but to completely go from one side of the line to the other requires some energy. Now, if I go to this part right here, I'll do this in blue, the melting line. Now when I go here, so I had this whole region like this, that is represented by here. And then this all of this, well, I'll put a crosshatch here. So all of this region, the solid and liquid, is right here. So there's a width of this line, which is represented right there. So if I take a magnifying glass, and it's like, oh, well, it's not exactly yes or no, liquid or solid, or vapor and liquid. It can be a mixture, and so the mixture stuff happens along that line, and when we draw the bell curve, that's what we see. Yes?
I think he's trying to ask about a constant temperature.
All phase change happens at constant temperature. If I go back to this curve, these are temperature isotherms. So if I go from state 1 to state 2, it all happened at a constant temperature. I went from 100% liquid to 100% vapor. I could say it's copper. I could say it's water. It happened at constant temperature. It also happened at constant pressure. Now, I can have a phase change where I have a change in temperature and pressure. Say if I went from here to here, but I would be changing pressure and temperature. So if I do a phase change at atmospheric pressure, the temperature is constant. Now, if I have a phase change where I'm changing the pressure too, then I might have a change in temperature. Or if I have a phase change at constant temperature, then the pressure has to stay constant. But remember, the width of this bell curve represents this region here. So if I have a pressure, 1 atmosphere, and I increase the temperature, I go from solid, so this whole region over here is solid, then I go to liquid, and then I go to vapor, and within this region here I have a bell curve. Within this region here I also have kind of like a bell curve. So this liquid solid mixture is this region. This is a liquid solid mixture. Along this line, along this line, I have a liquid-solid mixture. As soon as I get to the other side of the line, I'm all solid. As soon as I'm on this side of the line, I'm all liquid. Likewise, I'm all liquid here. As soon as I hit the side of the line right here, and I'm in between, I can have a liquid-vapor mixture, but as soon as I'm over here, I'm all vapor. And the energy required to cross the line or go from one phase completely to the other is related to the width. So a substance that contracts on freezing is this line, and a substance that expands on freezing, like water, expands on freezing is this one. So let's just draw one last line and we can finish up here. So let's do another example of myself, pressure, 1 atmosphere. Okay, so I have 1 atmospheric pressure, and I'm increasing the temperature. Because remember that if I draw one of these and then I come across, this is a constant pressure. So we'll say that this one right here represents 100 degrees C. This line right here is a constant temperature, isotherm. This is 100 degrees C. So if I'm over here, I have to be at lower temperature. So let's draw another one. I'll do it in red. And I'll do this one is going to be 50 degrees C. So I have my 2 isotherms, 50 degree, and so I'm keeping my system at constant pressure, but I'm changing the temperature. I probably should have put 0 degrees C somewhere here, but that I would have to be a little bit further down. So I have this. So this is an increase in temperature as I go from here to here. So again, I have my curve like this, and I'm increasing the temperature. Now I have this region and this region. All of this is liquid in this case, because this is a material that expands on freezing. And so now when I do that, I have this region here representing that, and this region here represented by this line. Temperature versus, or pressure versus temperature diagram, showing the phase diagram, triple point, all phases coexist, vapor, liquid, solid. If I just focus on this vapor line, I have a bell curve. To go from all liquid to all vapor requires energy. And so we expand this region, or some, okay, so let's do this one. Critical point up there. Now I'm right here. So at the critical point, there's no width to the curve, and you can, if you see, there's no width to the curve at the critical point. There's no longer a line up here, because it's indistinguishable. I can't draw a line. There's no way to determine if I'm liquid or vapor. If I'm all the way down here, then I'm way down here, and the width of the line is the greatest. And it requires the most energy to go from 100% liquid to 100% vapor. So these diagrams are nice for showing the different phases. When you do a lot of calculations, you need to know what happens as you cross that, as you change from one phase to the other. The bell curves tell you The changes in pressure, temperature, and specific volume, the widths are related to changes in enthalpy or the amount of heat you have to add or remove to go through phase change.